Welcome to this explainer. Today, we're decoding the hidden language of chemical concentration that completely surrounds us. Whether you realize it or not, the precise mathematical ratios of the liquids and gases around you are constantly dictating how your world works. Think about it. The source material hits the nail on the head right away. With this quote, "In normal life, we rarely come across pure substances. The air we breathe, the water from the tap, the brass on a door handle, it's almost all a mixture. And the safety and usefulness of these mixtures depend entirely on their exact composition." To figure out how these mixtures work, we're going to use this explainer as a sort of decoder ring. We'll run quickly through 5 sections: the chemistry of everyday life, the power of percentages, tracing the tiny parts, the chemist's toolkit, and why concentration matters. Okay, kicking things off with section 1, the chemistry of everyday life, mixtures and their impacts. So what exactly separates a life-saving medicine from a deadly poison? It sounds like a dramatic question, I know, but the answer literally comes down to a single word: concentration. The exact same chemical can save you or harm you, depending purely on how much of it is dissolved in a mixture. Let's look at fluoride as an example. Just 1 part per million of fluoride ions in our drinking water. That prevents tooth decay. It's a massive public health benefit. But take that exact same chemical, sodium fluoride, in a high concentration, and it is literally used in rat poison. No joke. The chemistry hasn't changed one bit, only the concentration has. And the margin of error here is wild. If you bump that fluoride up from 1 part per million to just 1.5 parts per million, teeth actually become mottled. That is an incredibly tiny line, which is exactly why having standardized, perfectly accurate ways to measure concentration is absolutely crucial. Moving right along to section 2, the power of percentages, measuring everyday mixtures. You've definitely seen these on the bottles sitting under your sink. Basically, there are 3 main ways to calculate percentage concentration, and it just depends on if you're mixing solids, liquids, or both. We've got mass percentage, volume percentage, and mass by volume percentage. Let's break these down. So for industrial stuff like commercial bleaching solution, we use mass percentage. You'll often see this written as W/W. This just means it's measured by the mass of the active component divided by the total mass of the solution, times 100. So that jug of bleach is precisely 3.62% sodium hypochlorite by mass. Now, when we're dealing with liquids mixed into liquids, like ethylene glycol for car antifreeze, we use volume percentage, or VV. You might think you just dump 100 milliliters of water onto 35 milliliters of the chemical. Actually, scratch that. It doesn't work that way. You start with the 35 milliliters of ethylene glycol, and then you add water until the total combined volume hits exactly 100 milliliters. Hitting that exact 35% volume mark is super important because it's what magically stops your car's engine from freezing solid in the winter. At that specific concentration, it drives the freezing point of water all the way down to negative 17.6 degrees Celsius or 255.4 Kelvin. Then we have the third type, mass by volume percentage, represented as WV. This is simply the mass of a solid solute dissolved into 100 milliliters of a liquid solution. If you ever look at a medical saline drip or pharmaceutical drops, this is the standard language pharmacies speak to ensure patients get the exact right dosage. Okay. Section 3, tracing the tiny parts. What happens when a percentage is just too big of a unit? Sometimes percentages are just way too clunky, like when a solute is present in trace quantities. Think pollutants in the air or that fluoride we talked about earlier. For those, it's way more convenient to express it in parts per million, or ppm. You just divide the parts of your component by the total parts of all the components, and then multiply the whole thing by 1,000,000. To put that tiny measurement into perspective, a liter of heavy seawater, which weighs about 10-30 grams, holds about 5.8 ppm of dissolved oxygen. It is a mathematically minuscule trace amount, and yet the entirety of marine life absolutely depends on that trace amount to breathe. Let's head into the lab for section 4, the chemist's toolkit, moles and specialized measurements. So first up is the mole fraction. In chemistry, a mole is just a standard unit used for a very specific, huge number of atoms or molecules. The mole fraction is pretty straightforward. It's just the number of moles of your target component divided by the total number of moles in the entire mixture. Chemists use this all the time for relating physical properties, like vapor pressure, or for describing gas mixtures. Okay, now we have to talk about 2 terms that sound frustratingly similar: molarity with an R
and molality with an L. Molarity relies on the volume of the solution, so moles per liter. Molality, on the other hand, relies on the mass of the solvent, moles per kilogram.
So why does that actually matter? Well, think about it. Volume expands and contracts with temperature changes, right? That makes molarity a function of temperature. But mass stays completely constant. So if a chemist is working with fluctuating temperatures, they're going to reach for molality every time to ensure their measurements stay dead accurate. Let's bring all of this together in our final section, Section 5, Why Concentration Matters, Real-World Impacts. Out in the real world, these applications are quite literally a matter of life and death. Take scuba divers. To avoid the toxic effects of high nitrogen under intense pressure, they breathe air diluted to precisely 11.7% helium, 56.2% nitrogen, and 32.1% oxygen. It's the same deal in hospitals. Intravenous injections have to be dissolved in water with ionic concentrations that perfectly match our blood plasma. These exact mathematical formulas are what sustain life.
The big takeaway here is that concentration isn't just lab trivia. It's the invisible instruction manual for our entire physical world. So next time you grab a bottle of bleach, some medicine, or antifreeze, take a second and look at the label. Which language of concentration is it speaking? Try to spot those hidden chemistry formulas, the WW percentages, or the mass by volumes that we decoded today. Thanks for joining me on this explainer, and keep exploring.